following presentation is presented by Aviation Maintenance Publishers. In this program, we learn about equipment setup and operation. Your narrators are Reed Nielsen and Ralph Jorba. Reed, what are the various components of a portable oxyacetylene welding system?
Ralph, the portable system consists of a cart to carry the cylinders around, a cylinder for oxygen and one for acetylene, regulators to control the flow from the cylinders, hoses to connect the regulators to the torch, and a torch to control the flame for welding.
And nothing else would be needed?
No, this is basically what we need.
What have we got here?
This is a oxygen cylinder. Oxygen cylinders contain 2200 psi pressure when they're full. They are a potential bomb, and if not handled properly, they can be extremely dangerous. The cylinder valve is covered with a safety cap which must be on any time that cylinder is in use.
And this is?
This is the acetylene cylinder. It contains liquid acetone and acetylene. The acetone will absorb 25 times its own weight in acetylene, making the acetylene stable.
Why should we only use it standing upright?
If the cylinder is laid down and the acetylene is attempted to be drawn off, you will pull off liquid acetone, and that will probably result in a fire. It should always be stood upright and should stand upright for at least 1 hour before any acetylene is drawn off the top of that cylinder.
I notice there are chains holding the cylinders to the cart. Why is that?
The cylinders should be secured to the cart so that they cannot be inadvertently tipped over and damaged.
What's going to happen now?
The welder is going to remove the safety cap. The cylinders are secured in the cart, and he's going to prepare here to put the regulators onto the cylinder valves. I might stress that that cap should be on there anytime those cylinders are moved or handled.
What's happening there?
The welder is going to open the cylinder valve for an instant to blow any foreign material out of that valve in preparation for putting the regulator onto the cylinder valve. Here he's selecting the oxygen regulator. He's looking to see that the seat of the regulator is clean, that it's free of nicks and burrs and any damage that might cause it not to seat.
What would happen if it seated incorrectly?
It would create a leak there. Not only is it costly, but it could possibly be dangerous.
Now, how tight does that have to be turned?
That regulator nut should be tightened only tight enough to prevent leakage.
Why shouldn't we use any oil?
Oil in the presence of high-pressure oxygen is explosive. We can result in a fire and an explosion that will damage the regulator.
And what's going to happen here?
He's again doing the same thing here, removing the safety cap and preparing this cylinder to put the regulator on. He will open the cylinder for just an instant to clear the cylinder and make sure that the valve has no foreign material in it.
If he were to put that regulator on, now I'll rephrase the question. I notice he's putting that regulator on and he's turning the nut to the left. Why is that?
All of the fuel gas regulators have left-hand threads so that they cannot be attached to a non-fuel gas cylinder. And in this case, your acetylene cylinder regulator has left-hand threads for this purpose.
So every gas cylinder has a left-hand thread. He was just pointing to that.
Every fuel gas cylinder has left-hand threads there.
Now here he's going to do what?
He's checking here the hoses, making sure that they're clean and free of damage or foreign material. He's installing the oxygen hose. The oxygen hose is always green. The acetylene hose is generally red.
And again, he's turning it to the left?
Again, the acetylene thread, or hose nut there, is left-handed. It is also left-handed where it fits onto the torch.
What would happen if inadvertently there was some foreign material and he went ahead and connected the hose?
It's possible that it would be blown into the regulator and damage the calibration on that regulator. Here he's installing the oxygen hose onto the torch. It has right-hand threads, and the acetylene hose has left-handed threads.
So it would never be possible to misconnect the hoses.
This is correct.
And again, these have to be tightened how tight?
Just tight enough to prevent any leakage on the torch.
What would happen if you applied too much pressure and just kept on cranking it around?
If you tighten it too tight, it would merely damage the seat, possibly pull the threads out of the nut.
What's he doing there?
He's making sure that the torch valves are off. He's going to check the adjusting screws on the regulator and make sure that they're backed out, that they don't have any tension on them, and then he will open the cylinders and apply the pressure to the regulator. If you watch the gauge carefully, you'll watch the one pressure gauge come up slowly. It's important that that cylinder be opened slowly so that you don't damage the calibration of the gauge. Now he's opening the oxygen cylinder all the way. It should be tight against the upper seat.
Why is that?
Because it is a high pressure valve. It has a double seat in it, and it will leak if you don't open it all the way. The one gauge on the right-hand side there has pressure. It is the cylinder pressure gauge. He doesn't have pressure on the one on the left until he screws the adjusting screw in on the regulator.
Now he's going to do the same thing for the acetylene cylinder?
This is correct. He's turning on the acetylene cylinder, turns it on slow, and lets the pressure come up.
Why does he only have to turn it a quarter to a half?
Okay, because the acetylene is the fuel gas here, it is important that you be able to turn it off in the case of an accident or a fire. And if it's open more than a half turn, it would be difficult to get off quickly.
What's he checking for now?
He's looking at the cylinders here to make sure that the regulators are correct. I might point out here that the rule of thumb for your acetylene valve opening is just enough to provide unrestricted flow.
Now he's turning that in?
Okay, he's going to adjust the regulator here, and you watch the working pressure gauge come up to about 30 psi. He has now applied that much pressure to the oxygen hose and torch. He's doing the same thing with the acetylene regulator. He's going to apply 10 psi there. Normally you will not use that high a pressure for welding with, but he's going to check this system for leaks.
Why would you never use acetylene at above 15 psi?
You notice that the regulator is actually redlined at 15 psi.
Right.
This is because it's unstable above that.
And if we were to go over to 20 and start operating at 20 psi,
it is possible to jar that cylinder and cause an explosion because of the unstable acetylene.
That looks like soapy water. What is he doing with that?
He's checking for leaks here with a soapy water. If he finds a leak, he's going to tighten that cylinder regulator just a little bit more and check it again for leaks.
Now, where does he have to check for leaks?
He needs to check any connection that he's made. Now, he's checking the hose here, and he found another leak. He needs to tighten that to the point that it will not leak.
And then he has to recheck it again?
Yes, he must recheck it after each tightening to make sure that he has corrected the leak. Here's a good example. He's retightening it, and now he's going to recheck this particular leak again. It still leaks, as you can see there, and the result, he needs to tighten that a little bit more.
How long will it take the experienced welder to set up a complete operation and be ready to weld?
It would take him approximately 5 to 10 minutes to be set up and ready to go if he doesn't have any problems. I might point out here, if you don't correct the leak, you're going to waste fuel gas. It is possible to accumulate acetylene and end up with an explosive situation or a fire off of it. He's checking the torch here for leaks to make sure that the torch is in good shape and that the nuts are tight. With the system all completed and no leaks, he is then ready to begin to weld.
Do you have to check that every day?
No, you just need to check it whenever you undid a hose, or when you took a regulator off. It should be checked when it's reinstalled.
He is doing what now? He brought the pressure down.
Okay,
Why?
he opened his torch valves, and he's backing off the regulators so that he can adjust to the working pressure he wants.
Now, why those particular working pressures?
He's adjusted it to 4 psi on both the oxygen and the acetylene. This is the recommended pressure by the manufacturer of that particular torch.
How did he just like that?
He had turned on some acetylene, lit it with a striker.
Why would you never use a match?
When the acetylene flows from the tip, it accumulates there, and if you light it with a match, you're going to get a flash flame there for an instant. It's possible to be burned quite badly from lighting the torch with a match.
He has just made the flame grow larger and then grow smaller again.
Okay, he turned up the acetylene, then turned on a little bit of oxygen, and has adjusted the flame to neutral. Turn off the oxygen first, then the acetylene. He's closing the cylinder valves here in preparation for shutting the system down. With the cylinder valves closed, he opens the torch valves and allows the pressure to bleed off of the system. Notice
he's brought them both down to zero now.
Right. On the oxygen, he's brought them to zero. He closes that torch valve, and he opens the acetylene valve.
Does he do the same thing again, bring them both down to zero?
Brings them both down to zero. Now he'll back out the regulator. That relaxes the diaphragm and allows the regulator to stay in calibration. And the system is ready for storage.
He's completely shut it down. This concludes our presentation on equipment setup and operation. Your narrators have been Reed Nielsen and Ralph Jorba. The following presentation is presented by Aviation Maintenance Publishers. In this program, we will learn flame adjustment and chemistry. So let's listen as Frank Jones talks about the flame.
First, we must turn on the cylinders of oxygen and acetylene and adjust the regulators. Remember that the oxygen cylinder valve is a double seating valve and should be turned open all the way. The acetylene cylinder should only be opened 1/4 to 1/2 turn for safety. This torch is a Purox make model with a number 4 size tip. The manufacturer recommends 3 to 4 psi working pressure for both the oxygen and acetylene. By turning only acetylene on and lighting with a striker, a bushy flame is produced. In this type of flame, the oxygen necessary for complete combustion is supplied from the surrounding air. When the oxygen from the air is combined with the acetylene and ignited, two different chemical compounds are formed: carbon dioxide and water vapor. In symbol, this would be written C2H2 plus O2 yields CO2 plus H2O plus heat, which is acetylene plus oxygen yields carbon dioxide plus water vapor plus heat. The equation must be balanced so that there will be equal numbers of carbon, hydrogen, and oxygen atoms on each side of the equation. As shown in this illustration, the equation is balanced so that there are 4 carbon atoms, 4 hydrogen atoms, and 10 oxygen atoms on each side of the equation. Also, from this equation, we notice that 2 1/2 volumes of oxygen are required to burn 1 volume of acetylene. This is determined from 5 volumes of oxygen to 2 volumes of acetylene for complete combustion. Also, from these equations, we see that heat is a byproduct of the reaction. The heat is used to bring the metal to molten temperature. The surrounding air from which we are taking the oxygen for this flame is made up of 21% oxygen, 78% nitrogen, and 1% other gases. Because the oxygen is mixed with nitrogen, the resulting flame is large and bushy. Considerable heat is also lost to heating the nitrogen. These two factors result in a flame of relatively low temperature and low heat concentration. Some of the acetylene may only partially combine, producing soot. To produce a flame of commercial value, it has been found that 1 volume of oxygen for each volume of acetylene should be supplied from cylinders. The additional 1 1/2 volumes of oxygen needed for complete combustion is supplied from the surrounding air. This flame is known as a neutral flame. The flame is made up of 2 zones, the inner cone and the outer envelope. The equation illustrates what is happening at the outer edge of the inner cone. Acetylene plus oxygen yields carbon monoxide plus hydrogen plus heat. 1 molecule of acetylene combines with 1 molecule of oxygen, yielding 2 molecules of carbon monoxide and 2 atoms of hydrogen. Since the oxygen in the primary combustion is not supplied from the air, the flame has a relatively high temperature, and the tip of the inner cone, approximately 5,800 degrees Fahrenheit, and is highly concentrated. The carbon monoxide and hydrogen are both combustible. They combine with oxygen from the surrounding air to complete the combustion and form the outer envelope. It should be noted that the outer envelope serves as a shield to protect the weld puddle from atmospheric contamination. To produce a neutral flame, light the torch with acetylene valve turned on, and then turn the acetylene valve open until the flame becomes bushy. Open the oxygen valve slowly. A long whitish-green feather, called the acetylene feather, will appear. Continue to open the oxygen valve until the acetylene feather is reduced to just the same size as the inner cone, or, in other words, until the acetylene feather just disappears. The flame is neutral. Let's adjust the torch again. Turn on the acetylene and light the torch with a striker. Turn up the acetylene until the flame becomes bushy. Turn on the oxygen slowly until the acetylene feather is the same size as the inner cone. If more heat is required, open the acetylene valve until an acetylene feather appears and becomes approximately a ½ inch long. Then turn on more oxygen until the acetylene feather again becomes the same size as the inner cone. This increases the BTU output of the torch. If the torch is producing too much heat for the work being done, the torch is turned down by closing the oxygen valve slowly until the acetylene feather appears to be about 1/2 inch long, and then turning off the acetylene until the acetylene feather is the same size as the inner cone. The torch will then produce less BTUs of heat. Always adjust the torch in small steps. If the torch is turned down too much, it'll cause the torch to pop and blow hot metal out of the puddle as the puddle begins to form. If the torch pops, a smaller tip should be selected. If more acetylene is supplied from the blowpipe tip than oxygen, the flame is said to be an excess acetylene or carburizing or reducing flame. The flame will now have 3 zones: the inner cone, acetylene feather, and the outer envelope. The acetylene feather contains free carbon that enters the steel as an impurity or unwanted alloy. Carbon will cause unwanted local hardening and possible cracking. It may also cause the puddle to have the appearance of boiling, thus making it difficult to control during welding. There are certain special procedures that require a carburizing flame. To adjust the excess acetylene flame, observe the inner cone. When the acetylene feather is twice the length of the inner cone, it is said to be a 2x reducing or carburizing flame. If the acetylene feather is 3 times the length of the inner cone, then the flame is a 3x flame, and so on. If more oxygen is supplied from the blowpipe tip than acetylene, the flame is said to be an excess oxygen or oxidizing flame. The flame will have only 2 zones, as does the neutral flame. However, the inner cone will have a more bluish tint and will be short and more pinched in appearance. Excess oxygen will cause burning of the molten metal and will leave the base metal brittle. An oxidizing flame can be used for special procedures. To adjust a flame to oxidizing, first adjust the torch to a neutral flame and then turn on a small amount of additional oxygen. The flame will have a harsher sound and will shorten slightly and turn more bluish in color. Make the oxygen adjustment small.
This concludes our presentation on flame adjustment and chemistry.
Could be eclipse.
No.
Oh.
Nice try, though.
Stand by.
The following presentation is presented by Aviation Maintenance Publishers. In this program, we will learn about puddle control without filler. Your announcers are Reed Nielsen and Ralph Jorba. Reed, what's involved in puddle control?
The welder must take a look at the molten metal that is produced by the torch. He must control that puddle to give him the proper penetration and the proper shape.
Now, what is the welder about to do here?
He's getting prepared to do some welding. You notice that he did have safety glasses on and that he has put on a pair of welding goggles. The welding goggles have a dark lens in them. This particular pair of goggles has a number 5 lens, which will prevent the high-intensity visible light and also the ultraviolet and infrared light from damaging his eyes.
Now, does the number 5, does that signify a certain level of darkness?
Yes. For oxyacetylene, it is recommended to use a number 4 or 5.
Okay, now he is about to do what here?
He is positioning his torch over a piece of plastic or practice metal. The torch is tilted back away from the direction of travel. Notice that he's holding the torch in his right hand and moving to his left.
Okay.
The torch has to be moved smoothly and evenly across that practice work.
Okay, why a particular angle on the tip of the torch?
This controls the heat input to the base metal. Notice in the illustration there, the torch can be varied from 30 to 60 degrees. Normally it's used at 45 degrees, but you can move it up as high as 30 degrees and as low as 60 degrees from the vertical.
And what happens if you were to go over or under that particular angle?
Okay, if you go above 30 degrees, you would produce too much heat in the base metal and perhaps blow a hole through the base metal. Now the side angle here should be 90 degrees. If it's tilted down as it appears there or too far to the other side, it will give you an improper bead shape.
And why is an improper bead shape so wrong?
Well, it can give you cold lap, it can produce discontinuities in the welded base metal. Here the torch is set at the proper travel angle. You notice in the illustration above that it indicates that to use a small circular movement. And now the welder begins to do that.
Why is the circular movement so important?
This is for heat control. As he moves the torch forward and up, it cools the puddle down and allows him to control the heat.
And is the height critical?
Yes, it is. He should never bring the inner cone closer than about a 1/16, and usually not more than about 3/8 of an inch away from the base metal at any time. So,
What would happen if the height was too high or too low?
Well, if he moves it too far away, the puddle cools too much. If he moves it too close, he can introduce impurities.
Now, this is an example of what?
Okay, this is an example of the bead that he's actually going to run for us. Notice the concave front. This is the back of the bead. Notice that it is actually penetrated clear through, and we have a bead on the back surface.
What do you mean by penetrated?
It means that we have melted the base metal entirely through the part.
Okay, now, it appears that there's something wrong in this one.
Okay, the top bead is a good bead. It was run proper. It has even penetration onto the back surface and appears to be a good bead.
What's wrong with the middle one?
The second bead was a result of lack of penetration. He didn't get enough heat into the puddle, and as a result did not penetrate clear through the bead. And you can see there's no penetration through that back surface.
Why the 4 holes in the bottom one?
Okay, those are caused from too much heat. are a result of actually overheating the puddle and blowing a hole through the base metal.
And that, other than being a bad weld, that completely destroys the metal?
Well, it doesn't completely destroy the metal, but it makes it a part that needs then to be repaired.
Okay, what is he about to do here?
Okay, he's lighting his torch and adjusting that torch to a neutral flame, and he's going to spend some time here actually adjusting it and getting it to exactly the right heat level that he wants it to be for welding this project.
And for this type of welding, he must use a neutral flame?
Yes, this is on a carbon steel, and the flame must be neutral.
What would happen if he used a wrong type of flame on this particular type of steel?
Both the oxidizing and carburizing flame would react with the carbon steel. Both of them would actually produce impurities in the weld metal and create a brittle weld.
Okay, and he doesn't seem to be moving it.
Right.
Oh, okay,
Watch
there he is.
in the upper corner there, notice the little glassy spot there. That's actually the puddle. The metal has become molten, and he will sit there until that metal starts to sag or penetrated clear through the part, and then he begins to move the torch, and you can see that circular movement there.
Now, what's causing the sparking that you occasionally see?
Okay, the sparking is caused by oxygen combining with the metal. It is actually creating their iron oxide, and that iron oxide is popping off of the molten puddle.
Now, I'm looking at the upper right-hand corner, the close-up, and I notice that he doesn't seem to be touching the puddle with the flame.
This is correct. He should keep that inner cone at least a 1/16 of an inch away from that, away from the molten puddle.
Okay, and in pushing the puddle along, he seems to be pushing it with the flame itself. Almost like painting.
Right, he is literally doing that, and it's heating in a concentrated point. See here, he's literally penetrated clear through that base metal.
Okay.
He's going to do it a couple more times for us so we can watch this technique.
Now here he's heating up the metal to make a puddle?
He's holding the torch at the proper angle, heating it up. Now if you watch the corner there, you'll see that little glassy spot start to appear.
Okay.
You don't want to get nervous and move too quickly on this. You want to stay there until it starts to sag, and when it sags, then start to move that torch.
Can those sparks cause any damage to a hand?
Normally not. They're very small. They generally won't bother your hands. However, normally you would be wearing a pair of light gloves to do this type of welding.
Now, the majority of the sparks seem to be coming from the bottom of the metal. What's causing that?
Okay, the atmospheric air is surrounding that molten puddle on the bottom side, and so we create more iron oxide on the bottom side of the puddle. It's actually an indicator of penetration.
Okay. Now, he's not actually pushing the metal with the flame. He's melting the metal, and that gives it that motion, the appearance of motion?
Right. He's bringing the torch down in close, and as the torch tip is brought in close, it heats the metal, and as he moves it forward, of course, the metal is melted ahead of him, and it actually allows him to penetrate clear through the part.
Now, in the bottom portion of the monitor, it appears that outside of the melting area, there seems to be almost an envelope of flame. What's causing that?
Okay, this is part of your secondary flame, the hydrogen and carbon monoxide combining with the air and burning. This protects that molten puddle from the atmospheric oxygen and hydrogen, and is actually helpful to the weld.
Now, would there be any nauseous fumes or fumes that would be dangerous to the welder?
Not generally on oxyacetylene welding, unless you're welding on material that contains zinc or some other contaminant.
Okay. How soon would the average student be able to do this particular process with the expertise that he's doing it? How long would it take the average student?
The average student will take 2 to 3 hours to learn to do this.
Okay. We seem to have a lot more sparking now than before.
Okay, the more sparks are a result of getting the puddle just almost too hot.
Okay, I notice he always uses pliers to pick it up.
You must use pliers. It's way too hot to pick it up by your hand. You notice here he's penetrated all the way through. Here is a properly run bead.
This concludes our presentation on puddle control without filler. Your narrators have been Reed Nielsen and Ralph Jorba.
Speed.
The following presentation is presented by Aviation Maintenance Publishers. In this program, we learn about edge welding without filler. Your narrators are Reed Nielsen and Ralph Jorba. Reed, are all of these three an example of edge welds?
Ralph, they're all examples. Even though the metal is bent or shaped differently, they're all examples of edge welds.
Now, what is he doing here?
He is going to demonstrate, give us a short demonstration on welding. Here he's doing it in the flat position. You can see the torch approaching the edge weld joint, and he will run it here in the flat position.
Okay. In edge welding without filler, since filler isn't used, exactly how are the pieces joined?
They're joined together by merely melting the base metal and allowing that base metal to flow together.
Okay. Why did he turn that particular piece of metal?
Just to demonstrate here that it can be done in the vertical position just as easily as it can be in the flat position.
So edge welding could be done in any position?
It's done in any position very easily. Here he's doing it in the horizontal position.
Even if you were welding with a piece of metal over your head, it could be done?
Yes, you'd use the same techniques for overhead welding. It's just a little more awkward as far as getting to the piece of material.
Now, I notice as far as his safety equipment goes, he's wearing are those goggles, safety goggles?
Those are welding goggles with the lens in them, number 5 lens for eye protection.
Okay. When he put his torch down, he didn't turn it off or any, well, he just turned it off there, but when he put it on the stand, he didn't turn it off. Is that acceptable?
He has an automatic lighter there on the corner of the table, and normally you would not set it down with the torch lighted.
Okay. What's he about to do here?
Here he has taken 2 pieces of practice material, lined them up, set them in a pair of welding clamps, and is clamping them together for welding.
And what type of weld is he going to give us now?
He's going to tack weld the corners of those 2 pieces of practice material together so that they will be held together.
Okay, he just lit his torch with what's that called?
He has turned on the acetylene, and now he's adjusting the torch to a neutral flame.
And the neutral flame is the flame that you use for welding?
He must use a neutral flame on carbon steel.
What would happen if he didn't?
If he uses an oxidizing flame or a carburizing flame, he's going to introduce carbon and oxygen to the base metal and give it impurities into the base metal.
Okay. Now, what's actually taking place in that little circle that we just saw?
Okay, if you watch it close this time, he is going to melt the corners together, and it actually forms the tack weld that will hold those 2 pieces of metal together for welding.
Now, how deep will that weld penetrate?
That will penetrate approximately 1/16 of an inch into that sheet metal.
So those welds are actually a solid piece, those 2 pieces of steel are actually a solid piece of steel for 1/16 of an inch.
That's right.
Okay, and here he's doing what?
He's showing us the side angle and the travel angle. The top picture indicates the side angle of the torch, and you notice that it's vertical to the joint.
Right.
The lower picture shows us the travel angle of that torch.
Why doesn't the metal drip? The molten metal, why doesn't it drip?
Well, we're heating that molten metal up to approximately 2800 degrees. The surface tension on that molten puddle holds it together so that it doesn't run off and doesn't drip away.
Okay, now he's about to do what here?
Okay, he's showing here the actual edge weld. He's beginning on one of the tack welds. He's going to heat that up to molten on that corner and begin to move it along.
Why does the metal spark sometimes and other times it doesn't spark?
Most of it is exaggerated by the camera. Generally it's sparking all the time, but to more sparks and sometimes than others.
Okay. Now what's happening in the circle?
Okay, in the circle there you can see a close-up of the puddle. You actually see the molten liquid puddle and it move along the edge as he moves the torch along. The two pieces are melding and actually flowing together to form the weld.
How long would it take the average student to learn how to do this?
The average student is going to take between 20 minutes and 30 minutes to learn how to do this particular weld.
And where would you use edge welding? What application would it have?
It has its biggest application with sheet metal devices. Could be used on a fuel tank or a toolbox or something of that nature.
Could you grind over that weld to make it smooth, make it straight?
You could, but it's not acceptable to do so.
Okay.
You'll generally grind through the weld and it will crack out or break along that weld.
Now here he's going to do what?
He's using a different shape here. The two pieces of metal have been bent in a cornice break and then brought together, and he's performing an edge weld.
What type of technique, if any, is he using here?
Okay, notice that he is not pushing the inner cone into the puddle, that he's moving it slightly back and forth to make sure that he's melting into both edges of that material.
Now in the previous lesson we saw he used a circular motion to make the puddle. How come he's not doing that here?
That circular motion was for heat control. Here he needs plenty of heat so that he can meld into the thickness of those plates. And he's just moving from side to side to make sure that both pieces of material are heated evenly.
Okay, so he's going from one piece of metal to another.
Right. Now there in that one spot, he almost lost the puddle, and so he backed up and started again.
What would have happened if he had lost the puddle?
He would have had a hole there, and
A blowhole?
no, it would have just been a pinhole, and if it was a gas tank, it would have leaked at that point.
Oh. Now what's he going to do this time?
Okay, he's setting up here another edge weld where we can watch it. This time he's going to be running it in the vertical position. Notice how he approaches the bottom corner using the same side angles and lead angles.
Is the vertical piece tack welded to the base plate?
Yes, that vertical piece is just tacked to the base plate so that it can be held in that position.
Okay.
See him move the torch from side to side, and you can see the puddle form as he moves up. You can see the molten metal actually flow.
So he's actually making one piece of steel out of the two different pieces?
On the edge, he is making one piece out of it.
Okay. Where would this particular technique be used?
It would be used on any of those parts if he had to weld it in the vertical position.
A water tower?
Yeah, any part that he couldn't roll over and do it in the flat position, he could do it in the vertical position like this.
So basically with edge welding you can do that in any position, any place the weld has to take place?
This is correct.
Okay.
Now you notice that he is melding evenly into both plates. Now
What would happen if he melted one side more than the other?
The bead would be off, misshapen. It would show that it was melted off more than one side, and it would probably be a weak weld because he didn't penetrate clear through in the center.
Is the shape of the bead critical to the strength of the bead?
Generally, it's an indicator of the quality of the bead.
And what's he doing here?
Okay, he's running this one now in the horizontal position. And you can see here he's starting to melt the corner. You must make sure that you have that puddle well established before you begin to move.
How does he know that the puddle is established?
He would know that it was established merely by looking at the width of the puddle and the fluidity of the puddle.
And how long will it take the average student to determine or to learn when he has a good puddle and when they have a bad puddle?
The student should have learned in the previous program how to tell when he had a good fluid puddle, but here you would merely watch the size of that molten puddle. It'll take him just a few minutes to know when it's...
Okay. Let me go back to the vertical weld for a second. Why do you start at the bottom rather than the top?
By starting at the bottom, we're able to get better penetration into that joint.
Why better penetration?
The penetration, if we started at the top side of that joint, would be hampered by the hot metal flowing forward in front of the torch.
So you actually work your way from bottom to top to stop the metal from flowing back down?
Right.
Okay. Okay. Now, the color of the metal itself doesn't have any bearing on it, on whether the weld is good or bad. It's just the puddle itself that determines that?
You can tell a little bit from the color, but most of it from the fluidity of the puddle.
Okay, so the puddle is the thing that every student must watch. That's the critical part.
You can never learn to really do a good weld until you know what that puddle's doing and how to control that weld puddle.
Okay.
Here he's approaching the end. As he approaches the end of the joint, you'll notice that it gets hotter on him, and he's going to have to speed up and move a little bit faster.
How do you know that it's getting hotter on him?
Well, it does this because of the bidirectional cooling, and here he's just run out of places for it to cool. He's run to the end of the plate, and the heat concentrates there, and the result is that he has to move faster.
Okay, now on edge welding, is it necessary that he go around the corner or just straight across the edge?
If he wanted to make a complete leak-free weld, he would need to go right on around the corner.
Now, what are these examples of?
Okay, these are 4 examples. The first one that he's pointing to there is an example of a good bead. It has even bead on both sides, it has even ripples, and it has good appearance.
The second one?
The second bead that he's got there is a result of having a gap between the 2 plates, and the metal wants to melt and flow down in between them, and it's difficult to do it that way.
Okay. Now, why was there a gap? Improper
Just
alignment?
improper alignment and setup.
The third one?
This is done because of misalignment of the 2 plates, and the last one was due to too much heat.
This concludes our presentation on edge welding without filler. Your narrators have been Reed Nielsen and Ralph Jorba. The following presentation is presented by Aviation Maintenance Publishers. In this program, we learn about running beads with filler. Your narrators are Reed Nielsen and Ralph Jorba. Reed, what is a bead?
Ralph, a bead is a deposit of weld metal on a piece of base metal. It's created with some filler. You see here an illustration of a bead. The upper illustration shows that the bead has even width to it, that the ripples on the bead are even. If you look at the 2 lower pictures, you find that it has an even height all the way along, and that it tapers smoothly into the base plate on both sides.
What is weld metal?
Weld metal is the material that you heat and deposit on the base plate.
Okay.
Now you notice that the bead here is 3 to 5 times the thickness of the material as far as its width goes.
Is the width of a bead important?
It is important because it determines the amount of penetration that you get into the plate itself.
Can you put too much bead or too little bead on?
Right. If you put too little bead on, you're going to get a lack of penetration. Now, here's an illustration of the side angle and the travel angle that as you approach it, notice that the upper picture is side angle. It's 90 degrees to the base plate. The travel angle is approximately 45. Your filler wire, which is similar to the base metal, comes in at 45 degrees from the other direction.
Are there different types of filler wires for different types of base metal?
Yes, there are. And here we're using an Oxweld 65 or an AWS RG60 filler, which is a carbon steel filler.
Now, is the depth of penetration critical?
The depth of penetration is critical. You want 100% penetration in order to get full strength out of a weld.
Okay, when you say 100% penetration, if we're talking about a piece of base metal 1 inch thick, you mean penetrating the complete thickness of the metal?
That's right. We will not actually sag it clear through, but we will penetrate the entire depth. Now, here's a piece of practice plate that he's setting on the bricks. We're going to do this without any backing on the back side of that plate.
Is backing critical?
Yes. It absorbs heat, and it gives you kind of a false security as far as welding goes.
Now, he's putting on his, he has his safety goggles on, and he's putting on his
welding goggles there
goggles.
with the shaded lens so that he can see the welding puddle and tell what he's doing.
And he's going to what type of a flame?
He again is using a neutral flame. Here you can see the torch held in his right hand. He's bringing it in at the proper travel angle, and you can see in the little circle there the red material. You will watch the base metal actually form a little glassy spot there.
Now, does he have to establish that puddle first?
He has to establish that, and when it's about 2/3 the size of the puddle that the bead width, he adds a little bit of filler. Now, I might point out here that he needs to make sure that puddle is the diameter of the desired bead before he starts to move, and that he has the proper buildup before he actually starts to add filler.
I notice that he's dipping the filler rod in and out of the puddle. Is the flame melting the filler rod, or is the puddle melting the filler rod?
The puddle is actually melting the filler rod. The torch itself keeps the puddle hot, and you dip that piece of filler into the center of the puddle and allow enough to melt off so that you get the proper amount of buildup.
Okay, how high does he have to hold the filler wire to keep from getting burned?
He would hold the filler wire approximately 6 to 9 inches away from the torch flame itself. And again, you may have gloves on or you may not, depending on what you're doing.
Okay, and how long will it take the average student to learn this technique?
To learn this technique would take some 4, maybe 5 hours.
Okay, where would this technique be used? In joining two thick plates of metal?
This technique is a technique to teach you to watch the filler. It could be used in a padding or surfacing technique, but mostly it's used here to teach you the coordination between the torch and the filler metal. The same technique would be used if you're trying to weld two pieces of material together, but here we're just running beads on the surface of the material.
Okay, how far does the bead go, and how fast should the bead actually be laid down on the base metal?
Okay, you would lay the bead down for the entire distance across the joint that you're working on here. Here he's going to run from approximately a 1/2 inch on one edge of the plate over to a 1/2 inch on the other, just for practice. He would move the torch at a speed that would keep him the proper bead width.
Okay.
If he moves too fast, the puddle will narrow up and your bead will narrow. If he moves too slow, it will get too wide and he can get a blowhole.
Okay, is the height of the reinforcement critical?
Yes, it is. If you get too much reinforcement, it acts as a stress riser. If you don't get enough reinforcement, you're going to have a weak joint.
What is a stress riser and why is that bad?
A stress riser would be a point of stress where you could possibly get a fatigue failure on it. I think that's probably a little beyond our discussion here, but it's important that you taper that bead smoothly into the base plate and that you allow the puddle to build up and have approximately half the base metal thickness.
Okay, and that is the thickness that you should always go for, half of the base metal?
I would say up to 1/8 inch thick material. Now you notice here on that he adds the filler to the puddle and that he removes it just a little bit. He's still in the secondary flame with that filler. If he pulls that filler too far away from the puddle, he will cool it off, and when he places it back into the puddle, it will actually chill the puddle and cause a cold weld.
Why couldn't he melt the filler rod with the flame?
If he melts the filler with the flame, it merely lays the bead on top and you don't get any penetration with it. So you must actually establish a puddle and then add the filler to that puddle.
It would just lay on top and you wouldn't get a good weld.
That's right. You wouldn't have penetration, you wouldn't have a sound weld.
Okay. Why don't you briefly review for us again the width of the bead, the height of the reinforcement, the depth of the penetration?
Okay. Depth of penetration should be 100%. The width should be 3 to 5 times the base metal thickness, and the height should be about half the base metal thickness.
This concludes our presentation on running beads with filler. Your narrators have been Reed Nielsen and Ralph Jorba.